Okay, so what we're going to do now is we're going to continue our coverage of Java structured concurrency. And if you recall what we talked about last time, we talked about two examples that used the structured task scope model of structured concurrency in Java. And we also talked about sort of a hybrid model that combined the executor service and its support for new virtual thread per task executor style of concurrency. And now we're about to talk about some alternative ways of doing things that are not using Java structured concurrency mechanisms. And the reason we're doing this is because I feel it's very important to be able to have a systematic way of comparing and contrasting different approaches to solve more or less the same problem. And this particular example will illustrate another way to do concurrency using Java's parallel streams framework. And this example will be largely I/O bound, or mostly I/O bound. We're going to download images from remote websites, which is largely I/O bound. We're going to do some transformations, which is not I/O bound. And then we're going to do some storing of images, which is I/O bound. So this will demonstrate how you can use parallel streams for I/O bound computations. This particular example we're about to look at is available here in the ex4 project in my Loom folder in my Live Lessons GitHub repository. So here we are in the ex4 project in my Loom folder. And if you recall last time, I'd shown you how we ran all kinds of different tests with all kinds of different mechanisms before we talked about structured concurrency. I'm going to run these tests because they take a while to run in the background. And what we're going to do now is we're going to take a look at the parallel streams implementation. And this is the way the parallel streams code is designed and implemented. So this particular approach is going to start by getting the list of URLs, which we store. And you can take a look at the list of URLs if you're curious. The list of URLs is up here. And these are a whole bunch of images from my website at this link. And this code basically just takes that list and creates essentially a list of URLs. We then take that list of URLs and we use a factory method called parallel stream. Now, we've talked a lot about streams, or we talked a little bit about streams in this course. You've seen lots of examples of streams. And remember, a stream is basically a chain of operations that will modify or filter out data that flows through the stream. And a normal sequential stream, which you get just by saying stream, is a stream that runs in a single thread of control. Parallel stream is a stream that runs in multiple threads of control. And it's beyond the scope of today's discussion to explain this in detail. There's a whole ton of videos on my CS253 website that explain how parallel streams work. But in a nutshell, what parallel streams do, and when you use this method, is it goes ahead and it takes whatever the data input is, which in this case is a list of URLs, and it splits them up into chunks, and then it feeds those chunks to tasks running in the common fork join pool. And the common fork join pool is basically the mechanism by which the processing of several different types of parallel operations occur in Java, including the structured concurrency stuff we've been talking about. So I'm not going to go into a lot of detail about fork join pool at the moment, but I'm happy to point you to other resources. Yes? Great question. So the question is the fork join pool platform threads? The fork join pool is indeed platform threads. And typically the way the fork join pool works is when you use it, it auto creates itself the first time it's accessed in a program. So it's sort of like the singleton pattern in a way. And it will typically create as many threads, as many platform threads in the fork join pool as there are cores on your machine -1. And there's a reason why it's -1, and that's because whoever calls the fork join pool pitches in and does processing along with the other threads. So by the time it all is up and running, there's as many threads doing computations in parallel as there are cores. There's also some other mechanisms available in Java, and we'll take a look at that actually here in a minute, that can be used to expand and or contract the size of the common fork join pool if operations block. And I'll actually talk a bit about that here in this example. So common fork join pool, lots of good stuff. Not really the focus of this course, but it's quite interesting. And it's used as the basis for lots of parallel and concurrent processing in Java. So we have ourselves a parallel stream. And then what we're going to do is we're going to go ahead and use some other stream operations. One of the cool things about streams is that you can use the same methods, the same operations like map and filter and so on, with either sequential or parallel streams. In general, they are interchangeable and they work just as nicely in one as the other. The main difference, of course, being if you use map with a parallel stream, then multiple operations will be transformed simultaneously, which is kind of cool. So what we're going to do here, speaking of transforming, is we're going to start by downloading the images in the stream of URLs. So we have a stream of URLs. You can actually see it up here, stream of URLs with this little hint. And then we're going to go ahead and download each image. And this is the code that downloads the image. And so you take a URL, and we're going to go ahead and download the image. So first, let's go ahead and take a look at what it means to download an image. It's really pretty simple. What we do is we create a new image object, giving it the URL, where it came from, and then we provide the content. And here's the download content method. The download content method takes the URL, and it goes ahead and opens a stream to that URL. So we have a connection, a socket that's open to that particular URL. And then while we haven't drained all the data from that socket, we read each chunk of data in to this buffer, and then we write the buffer to this output stream. And when we're all done consuming the entire contents of that resource at the URL that we gave, we convert that to a byte array. So we pass back a byte array. So we have the content, the image as a byte array, and we store that in this image object. So that's how we get the contents. Now here's the part that's kind of interesting. What we're doing here actually is we're downloading this content in the context of something called a blocking task. And a blocking task is a little helper class that I wrote based on some stuff you can find on the web. And it will arrange to download this image in such a way that an extra thread will be created in the common fork join pool, because we're going to be blocking the caller for the duration of the download. And while the blocking is taking place, there could very well be other things that could run. And if we only had more threads in the pool than there were cores, those threads could run too. So the problem is if we have a bunch of blocking operations and we only have as many threads in the pool as there are cores, nothing is getting done while we're blocking. But other things could be being done because you can overlap computation in communication or I/O in modern operating systems with multi-core processors. So here's how the call and manage block method works. We pass in the supplier, which in this case just downloads the file. We pass the supplier in. We create a new little helper object called supplier manage blocker. We'll look at that in a second, that encapsulates the supplier that was passed here. And then we go ahead and we say, hey, fork join pool, please go ahead and run this computation in a new thread by potentially expanding the size of the common fork join pool. Now, if there's an idle thread in there, it'll just go ahead and use it. But if there's not an idle thread, if everything's blocked, a new thread will be created. And it'll only live for a little while until it hasn't been used for a while. So that's what this does. It runs it in the common fork join pool and will expand it. And here's what the supplier managed blocker looks like. It's just a little helper class that's nested. It keeps track of the supplier to run and the result and whether we finished. And when the call is made to manage block, passing in the managed blocker, that managed blocker has a hook method called block that the fork join pool will call back. And what this does is this will go ahead and block, waiting to get the content, in this case, download the file at that URL, and then it'll update a flag and return the fact that we got that. So that's how we can download things in the background and expand the size of the common fork join pool. And when we're all done and we've got a result, we return the result, and all that does is just return whatever we downloaded, or whatever came back from the supplier. In this case, we were downloading. So this is a very cool mechanism that's provided in Java, in modern Java, Java 8 and beyond, in order to be able to temporarily expand the size of a otherwise fixed size thread pool, or largely fixed size thread pool. Now, one of the interesting things to note here, and that's the way the parallel streams works. If you had virtual threads, which was what we had when we did the structured concurrency approach, it would just create a virtual thread. We wouldn't have to do all these shenanigans with increasing the size of the pool and so on and so forth. But the parallel streams framework does not use virtual threads at this point. Perhaps at some point they'll expand it to do that. So what happens here is we have now a stream of images. When map returns, well, let me rephrase that. As map runs, map may appear at first glance as if it's going to wait until all the content is downloaded within that stream. But that's actually not how it works. It actually works by basically having each thread take content from the source, which in this case is this URL, and it applies all the operations in one fell swoop on a per data element basis in its own thread in the common fork join pool. So what's happening here is after map returns for a given image, we're then going to go ahead and apply another transformative operation. And this one is called map. And it's going to transform the images by making a call to a method, which is called a behavior, a method reference behavior, which is called transform image. So let's go look at that. So transform image is quite an interesting call. And you can see what it does is it takes the image, and then it goes and it gets a list of image transforms. So here's the list of image transforms. If we go here, you can see that there are several different transforms that we configure automatically when this thing starts up. So the list of transforms is a list of 3 transforms, a grayscale transform, a tint transform, and a sepia transform. Those are the 3 types of transforms. And we could add however many other ones we wanted to. And so what we're going to do here is for each of those transforms, we're going to make another parallel stream. And that parallel stream will then go ahead and in parallel transform the image as many times as there are transforms. Let's say there are 3 transforms, so it'll do 3 transformations, grayscale, sepia, tint, and so on. So that's how we do that transform. And you can see what we get back from transform image is a stream of images. So we have a stream of, so let's say just for the sake of argument, we have 30 images we download and we got 3 transforms. As the result of calling transform image on each image in our stream, we'd end up with a stream of streams that would contain 90 transformed images. So you can see if you look at the result from map with transform image, it's a stream of images. Well, that works quite fine, but it's a little bit awkward. We really would like a stream of images, not a stream of images. So there's 2 ways to do this. One way to do this would be to use flat map, but the problem with flat map is it doesn't support nested parallelism for all kinds of strange reasons. So instead what we do is we use map, which does support nested concurrency, and we end up with a stream of images, and then we go ahead and we reduce that stream of images with a special method reference called stream concat, and it basically flattens the stream. So it's kind of like flat map in a way, but it doesn't impede parallel processing. So we end up with a stream of images. So again, let's assume we had 30 images. Now we've got 90 images that have been transformed. And the last thing we do is we say apply map once again to store the images. And what that will do is we'll come down here. And once again, it'll use the call in manage block helper class, the method call in manage block on the blocking task helper class, in order to store the image. And those things will all take place in parallel, and it'll go ahead and expand the size of the common fork join pool if necessary to make sure that we're not blocking. And the reason that we're kind of obsessing with this stuff is that file I/O, like writing to a disk or writing to flash or whatever, will block. And therefore, we would like to increase the number of threads that can be running simultaneously. And all the store method does is just goes ahead and it writes the image to an output stream so that it's now residing on the file system. OK, so the very last thing we do here is call the toList terminal operation. And what this does is this terminates the stream, which actually just starts all the intermediate processing that we just talked about. And it'll collect the results into a list of downloaded, transformed, and stored images. And then we go ahead and print out how many images we downloaded, transformed, and stored. So that's the parallel streams version. And if you think back to the structured concurrency versions we looked at, there's a couple of things to note. The structured concurrency versions, for my money, have more ceremony involved. You've got to set up the try with resources block, and you've got to make the appropriate structured task scope nested subclass, like shutdown or failure. And we split up downloading, transforming, and storing images into separate methods. We didn't stream them together. And each method had a lot of ceremony going on, right? Try with the resources block, you'd have an array of futures to whatever we were dealing with, images or files, and we would have the join, we'd have fork, fork, fork in there, we'd have join, we'd have throw if fail, then we'd kind of collect everything together and so on and so forth. So there was a fair amount of stuff that was boilerplate code that you had to write over and over and over again. In contrast, the parallel streams version here, at least to me, is a lot more concise because we can kind of put it all in one chain, even though we split up these little operations, these behaviors in their own methods. I think it's easier to see at a glance what is going on once you get familiar with reading the streams syntax. So you can almost read it like just talking. You say, but get a bunch of URLs, in parallel, download them, transform them, and store them, and then collect the results. To me, it's more intuitive. But it's important for you guys to make decisions about what you like or don't like about any of these approaches in order to have an informed choice of what you think is the right thing to do for your experience and what you're trying to solve. Yes? Great question. So the question is, platform threads and a pool of platform threads, the fork join pool of platform threads is being used with parallel streams. It's also, of course, being used in structured concurrency, if you think about it, because under the hood are a pool of fork join threads, platform threads. They call them carrier threads, but they're basically platform threads with a few extra bells and whistles. So each virtual thread is just an abstraction that is multiplexed atop those platform threads. So it's actually very similar. It's just that the threading abstraction is moved up a bit in the hierarchy. And every time you fork, you get a new virtual thread if you're using the structured task scope model. Another interesting way to ask the question is, how does the performance differ? So here are some, this is just for this particular run. If we ran it again, we'd probably get slightly different results because, of course, this is actually downloading content over the network. So you're at the mercy of what's happening at the network at any given time. But this kind of gives you a sense of how one run worked. So you can see structured concurrency was very fast. Completable futures, which we'll look at shortly, is pretty fast. Parallel streams is also pretty fast, but a little bit slower. And then we have a couple of other approaches. And when I show you the other examples, we'll rerun the test and you can see what the difference is. But the good news is they all perform about the same. So it really comes down to your preferred style of programming. And if you embrace the functional approach, then parallel streams might be your cup of tea. If you embrace the reactive approach, then the reactive models we'll look at later might be your cup of tea. If you like asynchronous approaches, then the completable futures may be your cup of tea. If you want to stick with the more, I'll say, conventional, but it's the newest model, the model that uses structured concurrency, that approach with structured task scope could be a way that you might want to go. So the question that was asked is, how is context switching and so on done with virtual threads? And this slide will give you as good of an example as I can pull up off the top of my head, and you can read more about that at the link below. So here's what's happening. They have this thing called a carrier thread, which is just a platform thread with a few extra things. And you can see that, there's a pool of them. And you can see over here that we've got a bunch of virtual threads. So virtual thread 1, 2, and 3. And you can see at any given point, a given virtual thread is either running, waiting, blocked. So those are the three states that are shown in this diagram. And of course, when it's waiting or blocked, if it's blocked, it's probably blocked on I/O, waiting for I/O to complete. If it's waiting, it's probably waiting for its turn to run. We might distinguish between waiting and blocking depending on various characteristics. But at any given time, you'll see that only one virtual thread is running at a time. So and I think runnable means waiting to run, or it's ready to run, but it's not actually running yet. I'm not quite sure why they distinguish that. But at any rate, so you can see that this is the ideal is for the thread scheduler to try to pack as many virtual threads running on a carrier thread as possible. So think of it like sort of a bin packing exercise where the goal is to try to have things running all the time. But at some point, when something's running and it blocks, then there's a context switch, which is a lightweight context switch, because it's just basically moving that virtual thread from one queue to a different queue and then starting up another thread. So there's a very short period of time where we wait for thread v2 to relinquish its control and then turn it over to thread vt1. And then over here, there could be a period where something's waiting, like on a synchronizer or blocked on I/O. And so there might be a period of time where nobody can run. And so there's idle times. But the moving between virtual threads is very quick because it's just moving between queues. In contrast, moving from a platform thread, taking one platform thread that's running, suspending it, taking another platform thread that's ready to run, putting it on the core, resuming it, that takes a lot more time. And that's because it requires boundary crossing penalties in order to be able to move between user space and kernel space and back. Whereas the virtual threads don't have to make that trip into the kernel. They're just basically running in the context of a platform thread, and they're just moving between queues. So context switching of virtual threads is very fast, is the bottom line. Okay. Any other questions about that?